let's see, last time we introduced this idea of maximal ideal, right? Remember, an ideal, capital I, is maximal if you can never have a situation like this, where you have an ideal that is that properly contains I and J itself is proper, right? So if I is never properly contained in a proper ideal, right, then we say that I is maximal, right? So this is the situation, right, that we don't want to have when I is maximal, or that we don't allow when I is maximal. And we saw some examples and some situations. I guess we were working in Z, right? And we saw that if n is composite, right, then n is definitely not maximal. I don't know why I'm writing it as a quotient, right? But in Z, right, when n is composite, not maximal. When it's prime, it is maximal. And so our first result here, this is 27.3, is going to tell us something about, well, it tell us about maximal ideals and what happens when you do a quotient with a maximal ideal. So let's let R be commutative with unity, and let's let capital I be an ideal. All right, so then here's the sort of characterization of maximal ideals. So then I is maximal if and only if the quotient R mod I is a field. So that's a very strong relationship between the ideals and the quotients, right? Maximal if and only if, when you take that quotient, it's a field. And before we go to the proof, remember that example we did? We were looking at R bracket X mod the ideal generated by X squared plus 1, and we saw that that was isomorphic to C. And so what does that allow us to conclude now? It allows us to conclude that that ideal right there is maximal. And I really enjoyed this proof. So here we go. Okay, so in the forward direction, we're going to assume that we have a maximal ideal. So I guess we can write that. So let's assume that I is maximal, and now what we need to do is look at the quotient, right? Now, R is commutative with unity, which means that so is the quotient, right? So note that R mod I is commutative with unity, right? Because R is. So now what do we need to do? If we've got a commutative ring with 1 and we want to show it's a field, we need to show that every non-zero element is a unit. So we must show that every non-zero element of R mod I is a unit. So I'm going to pick a representative that gives us a non-zero element here. So that would mean that we're going to choose any element of R that is not in I. And let's call it, what do I call it here? Little a. So let's choose little a in R minus I. In other words, that tells us that the coset A plus I is not the identity coset in the quotient. And then I want to consider, I'm going to build a certain set. So let's say, and consider the set, let's call it capital J. And it's going to be all things AR plus I. So it's the set of all elements of the form AR plus I, where R runs through all of capital R, and little I runs through capital I. So it's kind of a strange set. I remember the first time I sat down, I think it's probably the first time I was teaching this class, and I came to this theorem and I wanted to prove it on my own. And I can remember sitting and struggling. Eventually, if you're trying to prove this, right, and I mean, it took me a while, but eventually I was led to consider this set. So this set is somewhat natural, right? Once you've seen the proof or gone through the proof, you'll say, oh, okay, I can see why you would consider this set right here. Now, we need to verify. What I want to do is show that J actually is an ideal. We show that capital J is an ideal. So let's pick a couple of elements. Let little j equal to AR plus I, and let's say J hat equal to A hat, no, not A hat, sorry, AR hat plus I hat be in capital J. And I guess I need somebody else outside, let's say S, and let S be in capital R. Then, if I look at J minus J hat, that's going to be A times R minus R hat plus I minus I hat. That is certainly something of the form in J. And if I multiply by S, so S times J, that's going to equal A times SR plus SI. Because I is an ideal, S times I lives in I, and so this is also an element in J. Okay, so that allows us to conclude that J is an ideal. So now, what else do we know? Also notice that A lives in J, right? So let's say since little a is an element of J. Now, why is that? Let's see. Choose R equal to 1 and I equal to 0. All right, so just choose R equal to 1 and I equal to 0. And that means that A is of the form of elements that live inside J. So what does that mean? So since this happens, we see that there is somebody in J that is not in I. So we see that J minus I is non-empty. Okay, so what do we have now? We have J as an ideal. All right, so let's say, so now, clearly, I is contained in J, right? Choose R equal to 0, right? And let I range. That means every element of I is inside J. So now what we have is I is properly contained in J, which is an ideal of R. And since I is maximal, we see that J has to equal R. Okay, in particular then, let's see, R has unity. That means that 1 lives inside J. So in particular, 1 is an element of J, and so let's see, what do elements of J look like? They look like this, which means that there's an element little r and an element little I, such that AR plus I equals 1. I call them R bar and I bar, so we can say, and so there exist R bar in capital R and I bar in capital I, such that 1 is equal to A R bar plus I bar. So now, if we multiply, so now, if we do A plus I times, what's going to be R bar? R bar plus I. Remember what I was doing? I was trying to find a multiplicative inverse for the coset whose representative is A. So we're looking for somebody to multiply, right, so that we get the coset 1 plus I. So now if we multiply this out, A plus I, or A plus I times R bar times I, that is A R bar plus I. Now little I lives inside, or little I bar lives inside there, so inside capital I, so this is A R bar plus I bar plus I, because there's no reason to put parentheses around this part here. But this is 1 plus I. Conclusion then, right? A plus I is a unit. So, sorry, I just erased that, but here's the idea. I mean, if you're wondering where this J came from, it came from thinking about what we want, right? We wanted something like this to give us 1. But we needed a little bit of wiggle room, right? Maybe our bar is not the perfect element, right? So instead, or it allows us to I don't know, it gave us this wiggle room, that little I. So that's why we constructed the J there. So hopefully, after reading through this proof, you can see that ideal J that we constructed is actually kind of the natural thing to do. Okay, so let's write a concluding sentence there. Therefore, A plus I is a unit. That's what we were trying to do. Okay, so now in the reverse direction, we want to assume that R mod I is a field. And then our goal is to show that I has to be maximal. So let's kind of get the setup here. So we'll say, and suppose J is an ideal where it properly contains our ideal R. And so if we want to conclude that, that I is maximal, we need to show that J equals R. Okay, well, if we have proper containment, that means that there is somebody in J that's not in I. So let's let, what do I call it here, little a be in J minus I. Well, okay, so then let's see, we know that A does not live in I, which means that A plus I is not the identity in this quotient. So we can say then A plus I is a unit. Okay, so that means it's got an inverse, right? So there is somebody in there, so let's let B, let B in R be such that A plus I times B plus I is equal to 1 plus I. Okay, so what does that mean? It means that AB is equal to 1 plus little I. Okay, so then AB is equal to 1 plus I for some little I in capital I. Okay, what am I trying to do? I want to show that J equals R. And one thing we know, if we can show that J contains a unit, right? Remember our theorem from last time, if J contains a unit, then we know that it has to be all of R. So let me see now. All right. A lives in J, which means that AB lives in J, and I lives in capital I, which means that I lives in J. So now, 1, which is AB minus I. AB lives in J, so does I, so this lives in J. So by our previous theorem, what was it, 27.1, so by 27.1, J equals R. Therefore, I is maximal. That completes the proof, and I don't know, I just think this is, it's not super high level, so that your I's cross, right? But it's still, it's got some meat to it. So this proof is, I don't know, it's fun, right? It's doable, right? Without making everybody's, head spin, right? But it still requires some technique. Okay, so let's look at some examples, and let me see what our time is here. Okay. So some examples here. R bracket x mod 1 plus x squared. So we know that this is isomorphic to C. What does that mean? So 1 plus x is maximal. We looked at this one, Z bracket x mod ideal generated by x. We know that that is isomorphic to Z. Z is not a field, right? So the ideal generated by x is not maximal. We know that if P is prime, so we already showed directly that the ideal generated by P is maximal. Here's another proof, right? We know that ZP is maximal. And so, so P, ideal generated by P is maximal. So here's maybe a quick proof now, right? Also, let's say when P is prime, and then let's use an N now, Z mod ideal generated by N, isomorphic to Zn. So the ideal generated by N is not maximal. We proved this directly, but now we can use our theorem to prove it also. So this is not maximal when N is composite. Okay, now let's do another example, one that we haven't seen before. So in Z bracket x, consider the ideal, let's call it capital I, generated by a couple of polynomials. I want them generated by the constant polynomial 2 along with the polynomial x. Right? So now we have a non-principal ideal, right? It's generated by these two separate polynomials, 2 and x. I mean, I guess I'm claiming that it's not principal. It turns out it's not principal, right? So there is no single polynomial that generates this. We'll actually prove that a little later. But for now, I'm claiming it's not principal. Now, what do elements in here look like, right? Just to be clear, so this ideal looks like the set of all polynomials of the form 2 times f of x plus x times g of x, right? So this is where f of x and g of x run through all of z bracket x. All right, so that's what the capital I looks like. Now, what I want to do, let's define phi from z bracket x to z2, right? So I'm going to define a mapping. I want it to be, so it's going to be like this. So by phi of f of x equals f of 0 mod 2. All right, so what do? Plug f of x, or plug 0 into the polynomial and then reduce mod 2. Now, this is a homomorphism. Here's a quick way to note, to verify this, is that this is actually the composition of a couple of homomorphisms. The first one is evaluation at 0, and the second one, reduction mod 2. So the composition of these two homomorphisms is a homomorphism. And so I'll just say check. You can either check it directly or verify that it's just composition. So I'll say check that phi is a homomorphism. Now, I'd like to identify the kernel. I mean, it's pretty clear. Hopefully, it's completely clear that it's onto. So, note that phi is onto as well. All right, I'll let you just think about that real quick. So now, I'd like to identify the kernel. So suppose that phi of f of x is equal to 0. Right? So what does that mean? Well, okay. Think about any polynomial. Oh, sorry. What would that mean? It would mean that when you plug 0 in, you have to get 0. Now, what kind of polynomials would satisfy this? Plug 0 in, reduce mod 2. Well, let's see. Let's just play around with this for a second. So we got a0 plus a1x plus blah 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 plus an x to the n. So first plug in 0, and guess what? All of that's gone. So when you plug in 0, all you have is the constant coefficient. Now, if it's going to be 0 mod 2, all that would mean is that a0 has to be even. All right? So then f of x has to be of the form 2n plus whatever. So plus a1x plus a2x squared plus blah, 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 down to, let's say, 8k x to the k. But guess what? This is equal to 2n plus x times a1 plus a2x plus dot, 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 plus akx to the k minus 1. In other words, right, where does this polynomial live? Right, it's got to be in capital I, right? So what does that tell us? So what that tells us is that the kernel of phi is contained in capital I. And now we need to show the reverse containment, right? So now let's pick. So now, if h of x is in, let's just write it out. So now, if h of x equal to 2 f of x plus x g of x, right? If we take somebody in capital I, then when we look at phi of h of x, that's going to be 2 times f of 0 plus 0 mod 2. And so, well, okay, 0 is gone. F of 0 is some number, but multiplied by 2, this has to equal 0. And so, what? I is contained in the kernel of phi. So now we know that I is equal to the kernel of this homomorphism. So by the first isomorphism theorem, Z bracket X mod the ideal generated by 2 and X is isomorphic to Z2. That is a field. And so by our previous theorem, that ideal has to be maximum. So by 27.3, the ideal generated by 2 and X is a maximal ideal. Isn't that fun? I totally love that. I don't know, sometimes maybe I get more excited than I need to, but that was fun. Now, there's an alternative proof of this. So, I mean, this is kind of a well-known ideal, right? It's used in various examples. And so there was a proof that the ideal generated by 2 and X is maximal using the first isomorphism theorem, but you can also prove it directly, right? So let me just give you an alternative proof. So alternatively, suppose I, which is the same I, right? Same, this, the ideal generated by 2 and X. So suppose I is properly contained in some ideal J, which is contained in Z bracket X, right? So we have some properly contained, or some ideal that properly contains I living inside Z bracket X. Now, if we take some polynomial h in J minus I, right, because we have proper containment, right, there has to be someone in there. And I should point out, notice I've done this a couple of times now. When I do my setup, right, when I'm trying to show that I is maximal, I will often say, suppose that I is properly contained in some ideal J, properly contained in R, whatever R is over here. And then my next step, because we have proper containment, that means that there is somebody in J that is not in I, and that's typically the next sentence that I write down. So keep that in mind. So then, then what? Then h of x is a polynomial of the form a0 plus a1x plus blah, 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 plus a n x to the n, where, now, what does it mean to live in I, right? I mean, what are polynomials that live in here? They are polynomials whose constant coefficient is even. That's what this does, right? So if it's not in I, then it has to have the constant coefficient of h has to be odd. So now we're going to define a new polynomial. So let's define k of x. It's equal to h of x minus 1. Here, that's the number 1 right there. So what am I doing? I'm taking this polynomial, I'm subtracting 1, which makes this an even coefficient, right? The constant coefficient now is even. And so this is an element of I, which is contained in J. So now I have what? I have h of x inside J. I have k of x. Oh, wait, do I want to say? Yeah, that one's in I. Yeah. I have k of x that lives in I, which means it lives in J. And so that means when I subtract them, right, they both live in J, J is closed under subtraction. So now h of x minus k of x, that's equal to 1. That has to live, I think I'd like to write it the other way around. So 1, and this is the number 1, is an element of, or the polynomial 1, I guess it's better to say. This is equal to k of x minus h of x. That lives inside j because j is closed under subtraction. And now, what does that tell us? Well, j contains a unit, which means that j is equal to the entire ring. So by our previous theorem, whatever it was, I don't know, 20, I can't remember which one. Okay, so I can't remember the number, but no, 27.1, I think. Is that it? Yeah, I think so, but change this if I got it wrong. 27.1, j is equal to z bracket x. And so what? Oh, so I is maximal. So two different proofs. They kind of use the same idea. I mean, this one obviously a little bit shorter, but I sometimes like just making use of the first isomorphism theorem. Oh yeah. Yeah, let's do one more theorem and then we'll wrap it up. So one more result here. So theorem 27.4. Kind of a quick and easy proof here. So let's see. Let R be commutative with 1. Then R is a field if and only if the only ideals of R are the trivial ideal and R itself. All right, so if R has no non-trivial proper ideals and it's a commutative ring with 1, then you get to include this field. We already knew one of these directions, right? So the forward direction, we know that fields have no interesting ideals. So the forward direction, so this follows from, I think it was corollary 27.2. Now for the reverse direction, what do I need to do? I need to show, what do I need to show? Oh, I want to show this field, right, obviously. So what do I need to do? I need to show that every non-zero element is a unit. So let's pick little a in R star, right? So choose a non-zero element of A. Then, okay, so I need to find an identity. So then, the ideal generated by A has to equal R, right? Because we know it's non-trivial. It's not the zero ideal because it has A in it. And so because the only ideals are 0 and R, we conclude that this has to equal R, and this is going to give us our inverse, right? And so 1 unity is an element of the ideal generated by A. Thus, R times A equals 1 for some R in capital R. And our conclusion, let me write it over here. Therefore, A is a unit. So now what do we know? Every non-trivial element, non-zero element of R is a unit. And that's exactly what we need. So, yeah, this is a good place to stop, actually. So we'll see you next time.